Hi, here we are discussing about a lightweight high-entropy TRNG using a quad cross-coupled feedback architecture. So this work introduced a lightweight high-entropy true random number generator TRNG architecture based on a novel quad-input cross-coupled feedback designs aimed at enhancing randomness quality. The objective is to develop an efficient and secure TRNG suitable for cryptography and security critical applications where high quality randomness is essential. Okay, the motivations arise from the need to maximize entropy and minimize hardware resource usages and maintain reliability across various process technologies. Okay, to achieve near ideal randomness, the designs utilize a quad input oscillating circuit. Okay, that is a QIOC. Okay, so that combines a self-driven jitter indicating a ring oscillators with a statistically connected cross feedback path to introduce metastability and non-deterministic behavior. So in the proposed extensions, the feedback mechanisms are further enhanced by introducing a static and dynamic feedback path using a D flip-flops and control based multiplexers. So these additions provided a configurability and improved entropy robustness under different operating conditions. The designs is described in Verlo-Hegel, simulated in modelisms and synthesized on Xilinx RTX7 FPGA using Vado. The evaluations metrics including area, delay and power are compared with the baseline QIOC based TRNG, and this result shows the while the proposed architectures include minimal additional area overhead in achieves a better performance in terms of delay and power consumption. So the feedback mechanisms contributes to the higher entropy generations and greater adaptability without sacrificing the lightweight design goals. Okay, so this makes the proposed TRNG as a stronger candidate for lower power cryptography systems and embedded devices and IoT applications required efficient and reliable random number generator. Okay, so now we can verify the paper. This paper is fully designed for the TRNG architectures, but this paper, the novelty is the quad cross coupled architecture with the feedback one. Okay, but here the paper they will be designed this architectures. Okay, so this is a TRNG standard architectures. One is a digitizers, post processing and TRNG architectures. Okay, so here the problem we are facing in the paper. Okay, so this two architectures is a novelty one. Okay, so the first architectures is a figure 2. It's a quad input oscillating circuit QIOC model. Okay, so it will be good one. Okay, so design. Okay, so here the 4 input they are taken, that is a quad they are mentioned in the architectures. Okay, and output is a single bit one. Okay, so here they are used number of hexas, 4 hexas they are used for 4 input and 4 D latches they are used. Okay, so here you can verify that. Okay, it's a latch based circuit. Okay, so this latch gate it will be generated with a single input and single output. Okay, not dual input dual output. Okay, so only single output it will be connected to the multiplexers. After that it will be connected to the XOR gate. Okay, so in between they are additionally added a noise source here. Okay, so this is a noise source they will be used, 3 input noise source and 1 input noise source. So using this noise source it will be generating a randomness errors. Okay, as per that randomness errors we will XOR the value and that value it will be generating the output the random variations. Okay, so here this quad input oscillating circuit will be used in the top model architecture. So this is the top model architecture, the proposed design with the 4 QIOC models. Okay, so here the 4 blocks it will be connected parallelly and the output will be sampled. After that it will be come with the XOR gate. Okay, so that is a noise module, sampler and post processing. Okay, so here what problem we are facing means the problem in the feedback. The feedback the output of QIOC 1 and QIOC 2, 3, 4, so it will be connect directly. Okay, so if it is come the QIOC 1 and 2, 3, 4, it's not a different model, it's the same model only they are connected. Okay, at the time of execution the QIOC 1, QIOC 2, QIOC 3, 4 it will be generating the same value of the output and the feedback also it will be come with the same value. Okay, so here output equal to 0 means the feedback also 0. So as per the 0, it will be generating any value, something, it will be generating 1 means the output feedback also 1. So it's maintaining in other 3 QIOC model also. Okay, so this is a problem we are facing in this architecture. So we remodified this architectures with a different level. Okay, so one is for feedback level, another one is for the dynamic feedback architectures we have made using this architecture. Okay, so for that proposed novelty, we choose this reference paper. Okay, the design of lightweight true random number generator based on Galileo's LFSR with a dynamic feedback path. Okay, so using this reference paper, so here also they will be developed a TRNG architectures, entropy, sampling and post processing, and this dynamic Galileo's architectures we have chosen it here. Okay, so this is a dynamic architecture, the feedback, this is a feedback path, this is a dynamic feedback path. So using select line, we can possible to choose either NOT gate or feedback. Okay, so this kind of techniques will be used in the dynamic feedback architectures, but direct feedback also we can possible to use. Okay, and additionally, if whatever we use feedback, direct or indirect feedback, okay, so we need a proper circuit in a QIOC, right? Okay, but here they are using only the D latch in the architecture. Okay, but here we used for D flip-flops. Instead of this D latch, we used D flip-flop, and the Q bar of the D flip-flop connected to the multiplexers, and Q we using for the feedback. Okay, and the Q using for the feedback means here we used for 3 input XOR gate only. Okay, so in the 3 input XOR gate, so this inverter architectures is a single bit noise source, it's a unwanted one. Why? Because it's generating 0 means 1 and 1 means 0 only. So instead of this noise source, we use this D as an input to the XOR gate. Okay, another thing, the noise source we have used for 3 architectures here. Okay, but every noise source it will be generating the same value of the output, so we reduce this 3. Okay, and we will come up with a 1 architecture. So this is all the novelties, and some more novelties also will be completed in this paper. Okay, this work we have developed in 3 models of existing and feedback method and dynamic feedback method. It will be generated in a Verla HDL and finally synthesized in a ATIC 7 using a Vado synthesis. Okay, okay, so this is our existing feedback architecture. Okay, so here the existing architectures as per the paper, the QIOC 1 and QIOC 2 4, so it will be good to generating a randomness. Okay, but in the top model architectures they make a mistake. Okay, QX1 2 3 4. Okay, so it will be generating the randomness, but here you can verify it, the QX1 2 3 4 it will be maintaining the same value, so it's come with a delayed. Okay, so that is a feedback, right? So FBO X1 X2 X3 X4, so that is a delay, so it's again given into the D flip-flop, that is a QIOC 1, right? So here the problem is, so it's maintaining the same value again and again. Okay, so if we XOR this value, okay, QX1 2 3 4 we will XOR means, so we will get 0 output only. For this problem, we solved this TRNG output error in the proposed architectures. Okay, so this is a feedback 1. Okay, so here we will get a proper output in the TRNG. Okay, so here we initiate a D flip-flop and we initiate different level of feedback, interleaving feedback, everything. Okay, so as per that we will get a different QIOC architectures in the sample 1. Okay, so as per this number of samples, we will get a TRNG in the proper randomness. Okay, so the same technique we used in the dynamic feedback architectures. Okay, so this is a dynamic feedback architectures. The dynamic feedback means it will be additionally integrated with a one multiplexer here. Okay, so where means in the feedback side, the feedback we are given, right? That feedback we need to give through multiplexers, and selection line also we need to configure. That selection line we configure from the noise source. Okay, and this RTL schematic will be generated. Okay, so here this one is a proposed feedback architecture. Okay, so here this is a QIOC model. Okay, so this is a top model. Okay, so here you can check the input A. input A, input A, input A, but here not we are given. Okay, so that is a method of interleaving. Okay, and feedback we interchanged everything. Okay, so here the B it will be connected, but here we are not used the B. Okay, the feedback we will be shifted. Okay, and inside of this QI OC module, okay, so we used instead of D flip flop, right? So instead of D latch we used D flip flops. Okay, here the Q using for the multiplexers, okay, and the Q bar using for the feedback. Okay, the feedback come with the X circuit. Okay, but here we are not used any multiplexers. Okay, but in the dynamic feedback architectures we plan to use for the multiplexers. So this is a dynamic feedback architectures. The top model it will be same for the feedback architectures, but here we used the multiplexers in the QOIC model. Okay, so here the Q it will be used for the multiplexer output, and Q bar we used for the feedback. Okay, so here the feedback come with the multiplexers. Okay, so the A input it will be generated from the Q, and B input it come from the QB. Okay, and selection line it will be used for the noise source. Okay, so here this is another set of the architectures. Okay, so the B and A. Okay, so this is a technique we have used in this proposed dynamic architecture method. Okay, so this work we have synthesized in Vado ATIC 7. Okay, so this is a synthesized results, LUT 24 flip flops, IO buff G. Okay, and this is a dynamic configuration. Okay, so here it will be take 3459 3. Okay, so these things we compare to the existing work, the base paper. So this is a base paper work, feedback and dynamic comparisons 403, 24 and 34. Okay, so here the feedback existing architecture, they are showing the results in the table 10. Okay, so here the proposed method it will be occupied 395 LUT, and the logic utilization is equal to 403, so that is LUT, and 584 is the registers, logic registers. Okay, so it will be mentioned, so we will use this for our comparisons. Okay, and compared to other previous methods, also we can take a comparisons for our publications. Okay, so the next thing is document. So here we have written an abstract document, base paper, improvement objective, proposed title, proposed abstract. Okay, and related notes. Okay, for this project. Okay, and finally come up with the literature survey and references. Okay, thank you.